Okay, thank you. Thank you very much, Josie and Lily, for your kind invitation. And it's my great honor to be here to share my team's recent work in this very unique, very good IIFC webinar series. So today my report is on the recent advances in the basalt fiber reinforced polymer composites and its key techniques and applications in marine engineering. Okay, so the outline will include the 4 parts. First, please allow me to give a very brief introduction about our research platform, the National Research Center for Basalt Fibers. And then we'll go to the materials and composites of basalt fiber. And after that phase, just to meet the marine engineering structure needs, some innovative application technologies will be introduced. Okay, so firstly, it's about our research platform. So this platform is the unique one in the field of basalt fibers in China, which focus on the basalt fiber production and application technologies. So this platform is founded in 2011, and currently we have 100 faculty members and graduate students who work in this platform. And this platform also supported by our 3 very good disciplines in Southeast University, the civil, transportation, and architecture. And then we also get some awards and leading some standard editing. Especially, we would like to also promote our research results for the real applications. So we work with not only the basalt fiber manufacturers, but also those application companies. Okay, so our team includes currently more than 20 faculty members and over 70 postgraduate students. So their fields cover structural engineering, fiber and composites, and also sensing and monitoring. And some members work just for the engineering applications. So with these teams, we can invent some technology from fibers to composites to structure members, and finally goes to the applications. And in this lab, in this center, we have several layers, the test facilities, like from the fiber production. We can get the raw materials and the drilled fibers in our center, and also can manufacture FRP composites, like the protrusion, like the molding, compression. And then we can test the materials, FRP material strengthening the structure members for their long service life under the fatigue, under the sustaining loads. And one of the future testing system is we can testing composite materials from several scales, like from the micro to meso to macro, by using different kind of fatigue, in-situ fatigue, and environmental coupling fatigue, and even the tremble with the environmental solutions to figure out the failure mechanism and to evaluate their service life. I think this testing facility is very unique. Okay, so next I will give some brief introduction about the basalt fiber. So this fiber, it features green materials. So it generates from volcanic rock. This is 100% natural occurring materials, and on the high temperature, like 1,500 centigrade. So this material offers similar properties to the carbon fiber and the glass fiber, like lightweight, high strength, corrosion resistance, and also some function ability, like the thermal isolation, electrical insulating, these properties. But its future is a green and low carbon material. So in China, it also regarded as one of the 4 high performance fibers. And the development of this fiber is supported by the country and the country's policies that support these materials as the strategic key materials. Okay, as this fiber is a natural occurring materials, so it met the problem like the variation of its raw material. So our work, one of our team just focus on how to make these materials very stable and how to make it be high performance and even for the mass production to lower the cost. So currently, these materials, we have the national code to classify the different property of these materials and make it to be a very good structure materials that can be used for engineering. Yes, okay, so after these efforts, we also invented some mass production facilities like this tank furnace production and make it to be an industry scale to lower the cost, to enhance the property and stability. And currently in China, the production is around 50 tons per year, and the production capacity is almost 6 times. And this market is also growing very fast during these years. Okay, so this basalt fiber has a very clear positions among the carbon and glass fibers because of its performance and also its cost to performance ratio. So it can just fill the gap between the carbon fiber and the glass fiber. So as a very good composition to these 2 fibers. And this also shows the green future of these materials. From its production process, we can see it's a very low carbon emissions, almost no other gaseous emissions. And these natural materials can have a very good recyclabilities. So after the waste fibers can directly move to the natural environment. And from the global market, we can see that these materials, this means is just use the raw material, use the fiber itself. And this percentage, 55%, that means use the composite based on the resin composite material. So most of the use are on steel. We need to use a composite. And also from the end use industry, our civil infrastructure is around 1/3 among all. And in recent years, in the automotive bodies and the electrical and the wind energy, this industry are growing also very fast. So our civil field is occupying around 1/3 among all of the use. And from the field of our research, so the interest in our basalt fiber is also growing. Now in the world, it is 85 times publications than the aramid fibers, but just 1/5 compared with the glass. But in China, the attention is higher than that of the world. So recent years still attract high attention, not only in our civil, but also other fields. Okay, so based on the development of this basalt fiber, so the next step, we need to enhance its properties based on the composite materials. So we not only just the fiber itself, but also need to consider the resin and also the surface between the fiber and the resin. So the purpose is to enhance the longevity and from the design concept to the enhancement method. And finally, we need to realize everything through the manufacturing technology. So for the longevity design of civil engineering, we need not only consider the structural behavior under the service load, under the static load, but also we need to consider long-term loading, such as long-term sustaining loading and also the fatigue loadings. And one key issue is how to evaluate the composite materials fatigue life, because in the past we just evaluated based on the like steel fatigue behavior. So is it suitable for composite materials? So with this thinking, so we developed a method that using a kind of in-situ observation tools. So by these devices, we can observe composite materials under fatigue loading on-suit observation. So we can figure out its propagation of the damage under the fatigue, and finally we can understand the mechanism of the damage on a different level of fatigue, such as the fiber fracture or the interface debonding or some mattress cracking. So with this method, finally we understand composite materials that's under the long-term fatigue loading. So if failure is different to that of the steel, so we need to propose a kind of a new method to give a different index for this composite material, like the 10 million cycles instead of 2 million cycles for steel fibers. So by these ways, we can make the failure modes of composite materials under the testing fatigue with the real fatigue loading. Okay, for the durability enhancement for the basalt fiber composites, we propose a kind of method from 3 stages. One is from the surface of the fibers, and the second is from the resins modifications, and finally is outer shear for protection of the composites. And also considering the fatigue and creep performance, some pre-tension for the composite materials, which shows a very good abilities to enhance the fatigue and the creep behavior. Okay, so with these efforts, we also promote some models to predict its long-term behavior. And finally, to make the composites with good quality, we need to understand the whole manufacturing process. And from the different stage, we need to enhance and eliminate the early stage defects during the production, so that we can make sure the quality of the composites instead of failure in some defects in the resins or some interface between the resin and the fibers. So that with this promotion, we can produce the durable and long life basalt FRP composites. This shows some typical production lines for the bars or for grid, and also for the profile, and also for cable system. So with this production, the current company use the basalt fibers have several types, like the chopped fibers enhance the concrete cracking behavior. And these macro basalt fibers, we also call the mini bars, can not only control concrete cracking, but also enhance its toughness. And this is sheets for the like repairing existing structures, and the bars, and this is special bars like for the special bars. The inner is steel bar, outside is FRP, and steel wraps and the grid, the cables, and this is a kind of a profile, some special profile like corrugated plates. This can be used for the internal lining strengthening, and also some other profiles. Another technology combined with the basalt FRP composites is by using the fiber optic sensors, especially the distributed fiber optic sensors. So these two materials, they can incorporate together. So the FRP can protect the weak fiber optic sensors, and the fiber optic sensors can give the FRP some functional abilities to give it self-sensing abilities, so that when we use FRP, we can provide more advantages compared with the conventional materials. Okay, here summarize the properties of BFRP composites. Is with the difference to the resin type, it can provide a high temperature resistance, because the fiber itself can resist around 800 centigrade, and the low temperature, so can minus 200, and also free source cycling, and the UV resistance, and different corrosion resistance. And also basalt FRP can have a kind of a low thermal conductivities, similar thermal expansions to concrete, and also electrical insulation. And also for some other functions, like it has the dielectrical consistence, and also the low magnetical permeability. So this is for some special buildings. They have some requirement for this kind of use. Okay, so with the basalt FRP, actually the engineering applications started in the 2008 around, and from the pavement to the buildings to the bridge repairings, and in the recent 5 years, more and more applications in the bridges and the tunnels, especially those bridges in the in this marine environment. So that's what I will focus today. And also for the basalt fibers, in the recent around 20 years, almost 20 years, so we built a lot of specifications or standards from the fiber itself to the composite materials, and also the applications in the different fields. So currently, totally is more than 50 standard what we can reference for its application. And also not only in China, but also some international standards like ISO, STM, CSA, all this information, and also Eurocode includes basalt fiber as one of the 4 fibers for FRP. And this is the latest ISO standards for the FRP bars and grids. Yeah, so these 4 type of fibers, CFRP, GFRP, BFRP, and AFRP. This is 4 very typical fiber composites. Okay, next I'll go to the applications, technologies we use. We use FRP composites in the marine engineering. So in China, in recent years, we have very many the national strategies to promote the applications to development, the marine environment, the marine engineering. So, and also the marine engineering structures, including those bridges, tunnels, buildings, and some floating structure members. So those structures still faces some challenges similar to that of the buildings, constructions in the mainland, but their environment is much more severe than the mainland structures. So the durability issues, the long life design, and the resistance to the disasters, and especially some cables in the marine structures, like the floating structures, like the pouring systems. This has some special requirement. And also for the marine floating structures, the energy transmission and energy storage is a big issue. So if the energy generated like by this kind of wind turbine. So if we like to transmit the energy to some other area, it will take a very high cost, and the efficiency is also low. So we think about in this kind of platform, we generate the electricity and the storage on site. But in this platform, the area is very limited. So if the energy storage component occupy a large amount of the area, so it will definitely affect the use of the platform. So a kind of energy storage and the structure integrated members or the component is quite neat for this kind of structure. Okay, so let's focus on the reason to develop for 6 type of FRP composites, like the bar, grid, and the macrofibers or the mini bars, cable profile, and corrugated plates. Okay, and for the infrastructure, marine infrastructure first. So we focus on the RC structure and the seawater and sea sand structure, cable stay bridge, and this is some special use for the FRC, concrete and internal truss bridge. So the first type of application technology is to use hybrid FRP composites with steel. So in the marine environment, so corrosion is the big issue. But if we use FRP to fully replace steel bars, it makes some problems about the cost and sometimes about the design method, especially under the seismic design. So one of the effective ways is to use hybrid way. So the FRP composites, FRP reinforcement can be laid out at outside of the structure. That means inner is steel bar and outside use FRP bar. So we can use FRP grids is better. So FRP grids and bars can control cracking outside and protecting inner steel bars, so that can enhance its durability. And also by using the linear behavior of FRP and with the bilinear behavior of the steel bars, we can achieve this kind of structural behavior. So it's will have the secondary stiffness under the large earthquake effect, and very good recoverabilities after those earthquake. So it not only can enhance the durability, but also it's the structure's toughness. Okay, and the reason to very good applications is to use the FRP grid to place on the outside of like the bridge tower at the concrete cover layer. So the grid is very thin, although it cannot provide a very strong structural contribution, but at this layer, it can very good limited cracking because the grid is bidirectional. So at this joint, it has a very strong joint because it's a FRP. The resin is impregnated in the fibers and under the pressure and high temperature, so it hardened to be an integrated one. It doesn't like the mesh or the some other fiber mesh, so it can very well control the cracking, two-directional cracking. Okay, so by using this method, especially for the mass concrete, like this kind of bridge tower, the diameter is very large and the thickness typically is over 1 meter, sometimes over 2 meters thickness. So this mass concrete, under the curing stage, the cracking typically is difficult to avoid. So by using the grid at a very thin layer, because it is free of corrosion, so can be very, very thin cover. And it can well control the cracking. This is the simulation results. Can see if without the cracking, without the grid, so the cracking will goes very fast. By using the grid, so the cracking can be well controlled. Okay, so this technology has been successfully applied in a very famous Huangmaohai crossing channel. So this is a very big engineering. It's one of the most important, the national engineering, which is connect a bridge with the Hong Kong, Macau, and Zhuhai. That's a very, very long bridge. This is a west link to that bridge. So when building this bridge, it felt a problem that how to control the early stage cracking of the tower, yeah, especially at the bottom stage. So the FRP grid is placed at this concrete cover. So the concrete cover is over 8 centimeters, very thick. But if we use the steel grids, so steel grids cannot place the very outside. So it still need 4 to 5 centimeters cover. So it cannot well control the cracking. But if we use the stainless steel, although in early stage it can control, but finally, because the differences between the electricity, so the stainless steel will accelerate the corrosion of inner steel. So it's still not a good solution to considering the durability. So BFRP grids. So this is a non-metal materials. So it is free of corrosion. So it can place very important role here to control the cracking. So here shows the construction site. See the black one, this is the BFRP grids. So it placed at the outside layer. So inner one, the green one is the coated steel bars. So after construction, almost no cracks can be observed. And this is an on-site observation. Okay, so with the grids, no cracking. But without the grids, it shows a very clear cracking. And also this grid, because it have the distance between the each one, so it can allows the aggregates go through. So this is a sample from the testing one. So can see the aggregates can go through the grids very good. It will not affect the property and the uniform of the concrete. Okay, so this technology is supported this Huangmaohai Bridge to be awarded as the George Rasson Medal, which is the highest award for the bridge industry. Okay, so this technology also be used in some other bridges, like the Chuanzhang Bridge. And although this is not for the marine environment, but it's still a very, very severe environment, like the high altitude and very big differences between day and night, and also the corrosion. Yeah, so this bridge and also this tower is very high. So in these two places, we placed the FRP grids to control cracking. So after construction, it also has the very similar effect to Huangmaohai Bridge. And also the application extended to the Shiziyang Bridge. This bridge is still under construction. And this bridge, I think, is the longest suspension bridge for the railway traffic and both use and the longest span, a very large bridge. So this is at the west ankle, this area, to use grids to control this, because this area, the stress is very complicated and very, very large. So we need to control it by the grid technology. So this is the current applications. You see, we place the outside layer. Okay, so after these three very successful applications, so currently this technology has been applied in over 20 major projects in China. Most of them are in the marine environment. So the total use of these grids is over 160,000 square meters. This is a quite large one. But this is just, I think, the beginning. Most of those applications are big engineering project. But for some other middle span or small span bridges in the marine environment still has these needs. So in the future, the applications amount will be increased. And the other applications is to use the basalt BFRP with the fiber optic sensors. So by the self sensors inside, it can sensoring itself. So this application is in the pier. So this pier is in the Dongwuyang Bridge. So this bridge features like the deepest water. So the pier length is very, very high. It's the world's longest one. So these self-sensing BFRP bars inside can monitoring the status of the pier, can provide the feedback, its deflection, its cracking, or the dynamic responses. So finally, it can give the guide for the construction to make sure the safe and exactly the position. And also the basalt grid not only can be used or the bar in the bridges, but also in the tunnel. For tunnel is kind of wall, and also for tunnels, this lining. Yes, so can use the grids or bars with steel hybrid reinforcement. So finally, it can enhance the durability to enhance the cracking control ability. Okay, the second type of composites is we call the mini bars, or we call the macro FRP fiber. So as we know that the steel fiber perform very good enhancement for the concrete by its cracking control, by its toughness. But in the marine environment, the durability is key issues. So it definitely, the steel fiber itself will corroded in some very severe environment. And also steel fiber, because it's self-weight, sometimes its construction ability is not so friendly. And we have some non-metal fibers, but this kind of micro one, so it only can enhance the cracking, but not toughness. So the invention of this kind of mini bars can meet this requirement. And also use the macro and the micro together. We can have a different 3-stage enhancement for the concrete. Like in the early stage, the microfibers can perform the cracking control. And the second stage, the macro one can perform its function. And the last stage, the slippage here and can provide a kind of the toughness for the concrete. So we did the experiment and shows that by using the macro fibers and sometimes we use hybrid macro and micros, we can achieve similar behavior to that of the steel fibers. The mechanical property is similar to that steel fibers, but for the view of durability, so it shows a much higher resistance to the corrosions. So here shows that the UHPC, we also can use these mini bars to produce. And still under the seawater, these corrosions. So after some dry wet cycles, you can see that for basalt fibers, its strength only lose 12%, but still fibers after same cycles, it will lose half of its strength. So that's in the very severe sea environment. So that shows the advantages of these mini bars. And also we can use seawater and sea sands to make this kind of ultra high performance concrete by using the mini bars. So in this case, for SSC concrete, especially the UHPSC, the non-metal one shows very good behavior, like the basalt one, this BFRP one, it shows a better one than the other fibers like the PP, because it's modulus. Its modulus typically is over 50 GPa, so it can provide a very good balance between the fiber fracture and also the slippage. So we can provide a kind of strength hardenings and this ductile failure. Okay, so for these mini bars to enhance the normal concrete or the UHPC, we also apply it in several engineering. This is in Shenzhong Channel. This is also a national major engineering project. So this application is in the bridge expansion joint. So at this joint, the cracking is a big issue. So with the minibar inside, so it can definitely enhance its cracking behavior, and also can resist the corrosions finally. And this is also in a port, it's Ningbo Zhoushan port. So in this port, we hybrid use the minibar and also BFRP grids to rebuild this deck, this port deck. So with these technologies, it can expect that the no cracking observed for the deck surface, so that the inner steel bars can perform very well under the long service life. And this is also a bridge in Jiangsu city, not very far from the sea. Yeah, so this bridge, the deck, the first time to use UHPC with the basalt, this is the BFRP mini bars. So this is the first use among China. I think it is also among the world. Use this UHPC with the basalt mini bars. So the construction abilities and also the strengths can achieve very high after a very short period of time. Okay, next is cable. So typically we understand the FRP cable is that the CFRP cable, carbon FRP cable. Although carbon FRP cable is a very good is a very good performance compared with the steel cables. But in some cases, we can use basalt fibers to also produce this cable, because it has a very high creep rupture strength. Typically, we call 50%. For carbon fiber, 70%. Glass fiber is around 30%. So it can be pretensioned for press dressing, and of course for the cable is also suitable. So it can provide a very cost effective compared with the carbon fibers. And also if we use the basalt fiber and carbon fiber or steel fiber hybrid them, so we can also provide a kind of vibration control, self-sensing abilities to satisfy the different spanning needs for bridges. Although the carbon fiber FRP cables can realize even longer bridges, like 10,000 meters. Basalt can sometimes realize like 3,000, 2,000, or 4,000 meters. So each FRP has it's suitable spanning for the bridges. So one of the key issues is how to anchor it. Similar to the CFRP, we also did a lot of study about the CFRP cable, but here we just showed the BFRP cable. We use a kind of variable stiffness, these kind of materials to anchor the FRP to avoid the stress concentration, especially the not longitudinal, but this directional compression to the fiber itself. Otherwise, it can only achieve maybe 60% of 70% of its strength. So by these ways, we can achieve more than 90% of its strength, this anchoring efficiency. So for the cable applications, so in recent year, we have very good opportunities to apply the self-sensing FRP cable, BFRP cable in the Zhangjin-Gao Bridge. So this bridge is the longest cable stay bridge in the world under construction. So its main span is over 2,000 meters, 2,300 meters. So for this bridge, the main span ankle area, we need to detect each cable force so that to make sure that the cable is under the good status. So by these ways, we use the BFRP cable. This cable is self-sensing cable to connect with the steel cable. So by this connection, okay, you see this is the anchoring of the main cable of the suspension bridge. So by this connection, so we can detect. So one of they have multi-tendons steel wire, multi-tendons. We connect one tendons so that we can testing its monitoring its strength, monitoring its temperature and humidity, so that during its service life, we can provide the data to monitor it. If the strength or temperature humidity is abnormal, so we can give some prediction. Okay, another type of products is profile. So profile can be used for build the truss bridge, but the conventional FRP profile may have some problem like the brittle failure, like the relatively low stiffness. So we use the multidirectional fiber sheet, this design, multidirectional design, to make this protruded FRP profile can resist the shear strength, can enhance its connection behavior. And also by using the hybrid method, like the carbon fibers, to enhance its stiffness. Because after multidirectional design, so the stiffness will be lower, so that we can balance the loss of stiffness and also achieve the high shear capacity. Okay, so test results also demonstrate that this is the shear strength of the composites. So by this multidirectional design, so we can enhance 2 or 3 times. And by using the carbon fibers, we can enhance, because this is the after multidirectional design, the stiffness is low, but we enhance just 1 layer of carbon fibers, so we can enhance its the modulus. So after this design, at joint, if we use the bolt connection, so we can find it fell from the brittle shear failure to this ductile bearing failure, so that the capacity, the ductility has been obviously enhanced. And also we can propose some optimization design for this kind of profile, and through the industrial protrusion technology with the multidirectional fiber sheets, and this is fiber rovings, and integrated them together to produce this profile with this design. So finally, we can build this kind of truss structure and to test its behavior. Okay, so it's like this kind of failure instead of this kind of shear failure. Okay, so this enhanced BFRP profile so has been used in some truss bridge. So this is our kind of bridge. Okay, so the BFRP corrugated plates is a special form of the profile. So by using this corrugated plates, so we can replace the currently used like the concrete like the steel plate strengthening for the tunnel lining. So these ways can not only enhance the durability of the tunnel, but also it is a kind of electrical insulation materials, especially for the railway tunnel. It has definitely very important this function. So we can see that this is the corrugated plate. This is the lining concrete. This is some mortar, like PCM or some other mortar materials to fill it, to connect to these two materials. So to develop these products, we have this technology, use the compression molding, and how to optimize this wave. we tested from the materials level, the plate level, and also how to connect it very effectively. So here the multi-directional design perform very good guide for this connection. So with this method, we strengthening the tunnel lining, so it can achieve very good structural enhancement from different stages. And currently, real engineering is designed according to this new technology, and will be realized in the next 6 months. Okay, so aside from the conventional infrastructure like the bridges, tunnels, those structures, so in the marine environment, marine engineering, some other like the floating structures, so currently is received a very high attentions. So many like big countries and people put a lot of attention to the development of new type of structures for the superstructure and also floating system platform, and even for the stability, the mooring system. So we also focus on this area, but this is most of them are still under this experimental stages and not in the real application. So one of the application is for the PV bracket. So PV bracket typically is used steel, and very seldom to use stainless steel, but just use steel with some coatings. So in the mainland, when the corrosion is not severe, so it's very difficult to use the FRP bracket, the PV bracket, because of the cost and also the efficiency of the connection. But in the marine environment, the cost, the corrosion is controlled. Sometimes control is service life. So to meet these needs, we developed a system of this PV bracking and tested its structural behavior, satisfy the deflection needs and the connection by some stainless steel part. So after careful calculation for the cost, so if in the marine structures, marine ocean environment, so we can replace the coated steel with FRP bracket with cost effective. If we just consider the initial cost, we still have a little bit advantages. But if we think of the long-term behavior, the advantages will be very large. So this kind of PV bracket is possible to replace conventional materials, steel or stainless steel, under this environment. But in the mainland, it's not possible due to the cost limits. Okay, and also for the wind turbine tower. So wind turbine tower, so for the blades, so for blades, typically the carbon fiber and glass fibers achieve very good functions. But for tower itself, currently for like floating, if we just use steel and RC tower, sometimes it's difficult to achieve very high one. So a kind of a hybrid turbine tower, this tower recently attracted very high attentions. So to realize this kind of steel and concrete hybrid tower, so for the concrete part, the UHPC with the prefabricated and assembled way. So with the mini bars and the steel FRP bars, so can realize this kind of very competitive structural behavior and economical issues. And also for the floating areas. So with UHPC with to those box shape with BFRP grids, UHPC and BFRP bars, so they work together to provide this floating area. And also for the floating area, sometimes the crash control. So these are also very important issues. We need lightweight, economical friendly to control the cracking, to resist the cracking. So we recently developed a kind of integrated manufacturing ways with this kind of harmony cube structure by 3D printing. So this the resin. Currently, we're still in the experimental stage. So the resin with the chopped basalt fibers, and the latest one we use the continuous fibers to predict this kind of harmony cube structures to resist the crushing. And this other innovation is to invent this kind of multi-stage harmony cube, not in just one stage, one layer, but in different layers. So by this kind of design, so its dissolvation strength and crushing force, the crushing energy can be enhanced greatly compared with the conventional design. And also we have different other type of design of the cross-section harmony cube cross-section. But this multi-stage design can achieve better performance compared with the other ones. So that's also the advantages from the materials design and the structure design is an integrated one. Okay, so the last issue is for the energy storage. So for this platform, if we would like to save the space that in this platform, we need to consider some structural members with the ability to store the energy. So considering the basalt fiber composites, recently we developed a new type of structural energy storage integrated FRP composites. And at the same time, we're also considering the cementitious composites as the same function, but another issue. And how to realize this energy storage composites? We use the basalt fiber, the fabric, the sheets as the separator for this storage component. And the electrochoid use the conductive basalt fiber fabric. So the basalt fiber itself is the electricity insulation materials. So we can use some modification like a carbon nanotube, this kind of materials, or these PPY, these materials, to modify the surface of fiber itself to make it to be conductive materials. And also we can also do some modification for the epoxy resin. So epoxy resin here can be used as an electrolyte. So with these three components, that we can realize this energy storage component. So this one and also has a very good mechanical property. So at the same time, it has this energy storage ability. So after modification, basalt fiber can achieve not as good as carbon fiber, but it's still similar function. And also, not only for the basalt fiber, we can also treat it the epoxy resin by the PEG. But PEGs make the epoxy resin very soft, but it's enhanced its ionic conductivity, greatly enhanced. So make it to be this kind of electrolyte materials. So with the electrolyte materials, with the isolation, and also with the electrode conductive basalt fiber, so we can produce this kind of energy storage component. And finally, is for the pouring system. So pouring system is not only used for those platform, but also for the mining ship, this kind of structure. Yes, so it can provide a very good durability, and also we can make it like a can be bended, So this is very important. So typical FRP cannot be bended very well. So we need to modify the resin. We need to make it to be twisted, so that by this way, and also we do some optimization about the friction, about the diameter, about the twisted angle. So finally, we can make FRP to be easily bended, make it to be flexible rope. It's not a fiber rope, it's a FRP rope. So the durability, the wearing ability can be greatly enhanced. Okay, so I think that's all of the content I report now. So finally, a very brief summary is basalt fiber actually is growing in high performance structure materials. So after we enhance its mechanical, the production technology, currently it can be used for structure. And for its composites, and after several methods to enhance its quality, so currently the grid mini bars cables are developed very well, especially the self-sensing product. So focus on the marine engineering, the hybrid FRP to steel reinforcement, the multi-directional fiber profile, and the mini bars used for the concrete or UHPC meet very good chances for future applications in the marine engineering. Okay, here is some publications related to today's report. And thank you for your attention. Thank you.